Alright, so let's learn about square roots in this video lesson here. Alright, so to begin, as a brief introduction, there's a number 9 right here with that symbol. So number 4 with that same symbol here, and number 36 here with that same symbol. So the way it says, this is the square root of 9, and this reads the square root of 4, and this reads the square root of 36. And so as far as the calculation, the square root of 9, and square root is not waited until college level to learn about square root, or a college algebra course to learn about square root. They start introducing square root like since the elementary school right there. So the square root of 9 is 3. So allow me to remind some very simple results. So the square root of 9 is 3. Square root of 4 equals 2. The reason for that, the reason that square root of 9 equals 3 is because 3 squared. So the reason because 3 squared equals 9. The square root of 4 equals 2. The reason for that is because 2 squared equals 4. And so same way right here, square root of 36 equals 6, because 6 squared equals 36. Okay, and so that's a brief introduction of what a square root is. So, and anyone, like I said, anyone viewing the lesson here doesn't have to wait until a formal college math to know what a square root is. And so now, in that way, let's brief through a definition of what a square root is. So, simplest way of putting it, the square root of a number, of any number, comes out with a value if the square of that value, so in the way how it says right here, square root of a equals m if the square of m equals a. That's the simplest way of understanding what a square root is. And so again, let me repeat in the way how I was doing it earlier on the board as a demonstration. The square root of a number equal to a value if the square of that final value equals to the number a from the beginning. And so for that reason, now formally speaking, square root of 9 equals 3. And that was because 3 squared equals 9. See, this was a, the square root of that a equals a number. That simply is because the square of that final value equals 9, the number inside of our root. And so similarly, square root of 4 equals 2. That is simply because 2 squared equals 4. And needless to say, square root of 36 equals 6. And that is because 6 squared equals 36. Alright, so now we know basically what a square root is. Allow me to bring in a couple of computational problems. And along the way that we study through the problems in this problem number 1 right here, then we are going to recognize and learn some more details about square root right here. So a problem to me, the problem that being brought up here, these are all the problems that help us to discover, to explore more properties of the square root of the particular kind of operation that we're learning right now. So let's look at that. All right, so in this problem, how about I'm introducing square root of 25. So it's not hard at all for anyone. It's very easy for anyone viewing this lesson. Square root of 29 comes out 5. Needless to argue about that. How about square root of 3? This is where things is starting to get a little challenged, because take my word carefully. I am not saying that the answer, the final value, does not exist. But now notice that the 3 here is not a perfect square. The 3 here is not a perfect square. Whereas over here we had square root of 25 being a perfect square, and that's perfect square, the perfect square of 5. We can recognize that easy. Whereas here we can't recognize it that easy. And so when values are not easy to recognize as a perfect square, or as a matter of fact, when values are recognized as non-perfect square, then we need to use a calculator. So I'm not intending to teach you how to use a calculator here, but I just want to show that, for example, what I had on the board, square root of 3. And so now I enter that into a calculator, and we hit enter. And we do have a value, but keep in mind the value now is no longer a nice, nicely recognized value. It's a 1.73 something. And so for that reason, in the way how we have seen that on the computer screen right there with the calculator, with some calculator, I use some calculator. You can use any calculator in these days has a square root functionality. But the point now is that we don't like working with lengthy decimals. So now instead of getting the real final value, of course, I use a calculation demonstration just to show that there is a value for square root of 3. The square of that 1.7 and a lot longer is 3. But there's no reason to write down that lengthy. So now it's been a long time tradition that we just rewrite. So a root that we cannot, the square root of a number that's no longer a perfect square, the root of a number that's not a perfect square, we can just simply leave that as the exact expression, square root of 3. So we leave that here, and it may be early right now, but I call a square root like this, an irreducible square root. Right, because from here now if we observe that a little more closely right here, taking the square root, the number inside the square root was a square, it was big number, and then after taking the square root, it came out being a smaller number. And another thing to pay attention to, that after we take the square root, we no longer have to write the square root symbol anymore. Because remember, the square root now is an instruction. What we do with the symbol here is an instruction telling us what to do to the number 25. So square root of 25, once we have come out with that value, we no longer have to write the square root symbol. But here in this case, square root of 3, we sadly we didn't recognize a perfect square that goes into 3, and that represents 3. And so we have to leave it the same way because we want to avoid writing decimal values. All right, so in that case, we aside from those perfect squares, which are easy to take square root, there are a lot of cases, there are a lot of instances where you run into, for example, square root of 10, we have to leave that as square root of 10 in exact expression. And again, this square root of 10 here is another example of irreducible square root. How about square root of 5 right here? Again, I don't recognize 5 here as a perfect square. So again, I am writing that as just exactly the way how it was started. Keeping in mind that these are all having some actual value if we use a calculator. But once we decided not to use a calculator and leave things in exact expression, then this is the expression for that. And this is another irreducible square root. And so, drawing out some experience from that, the problem that I've demonstrated through the 3 little problems, the 3 little calculations, then I need to mention that a lot of times when you're working with square root here, then exact expression preferred. All right, and you see exactly what I meant by exact expression is preferred, because you've seen that when I was demonstrating taking the square root of 3, where 3 was not nicely a perfect square right there, then using a calculator to take the square root of 3, we are running into a lengthy and extremely lengthy decimal right there, and that's what we're trying to avoid. And so in that way, we have no other choice better than writing out square root of 3. We know it exists, the actual value exists, but we write that in exact expression as the final square root of 3. And that's what I meant by exact expression from now on is preferred. All right, so let me bring in another problem right here. And as we go through these problems right here, we keep recognizing more and more properties and more details, those fascinating details about square root. So now in this problem number 2, allow me to bring in 2 little calculation problems right there. All right, so right here in this first little problem, I want to compute what about square root of, and the way it reads, square root of -4. Okay, so if we're rushing into the problem, we will think that the answer is -2. Okay, but here's how you can check yourself right here. Remember the definition that we've seen earlier, and we should know that by heart up to this point. If this value turns out to be negative 2, if taking square root of negative 4 turning out to be negative 2, it means the same as when you square negative 2. We got to get back to negative 4. That's what I was saying as a scenario. If this was true, then squaring the number according to the definition, then squaring the number, the final output has to ensure landing back to the original number inside the square root. So supposedly, square root of 2 all square must equals negative 4. But is this really true right here? It's not true. This is not true. And so guess what? This minus 2 is not the answer to square root of negative 4. Then we can think about maybe square root of 4 is still equals to 2. But obviously, again, we can quickly check. 2 squared is obviously equals to 4. Not negative 4. So this is wrong right here. 2 squared is not equal to negative 4. So we tried 2 attempts, but it didn't work. All right. So now also we sit back and think a little bit, and now we found out another truth. It is impossible to take the square root of a negative 1, and we won't be able to find an answer. We won't be able to find an answer anytime we're taking the square root of a negative number, at least for our beginning of the journey right here. Then for our start of the journey right here, then we cannot take the square root of a negative number. Okay. All right. And so what about right here in this same problem? We are brought into another simple computational little problem right here. How about square root? Let's calculate the square root of 0. Now, indeed, square root of 0, think about it. When you square 0, the answer does come out 0. So taking the square root of 0. See, if 0 squared equals 0, then the square root of 0 equals 0. So indeed, we do have an answer for the square root of 0 equals 0. All right, so from the 2 little problems that I brought up in this problem 2 right here, so that we can discover some more properties of square roots right here, allow me to get back on the computer screen to show some generalized results right here. All right, and so now the statement on my computer screen here is indicating that 1 cannot take the square root of a negative value. You see, this statement here is a very powerful statement. It guarantees that you just simply cannot take square root of a negative value. Keep in mind, I brought in that additional little problem about taking square root of 0. That's still consistent with this truth right here, this fact right here, because 0 is not considered as a negative value. And so we were still able to take the square root of 0 just fine. So again, the highlight here is that 1 cannot take the square root of a negative value. And so another way of saying that, it just, for any time we are taking the square root of a here, it is required that a has to be greater than or equal to 0 for any square root of a. That's how we should put that in a box, as that deserves our attention. All right, so now allow me to bring in the third problem. And again, in this problem, we are going to put in a few computational problems so that we can understand more properties, even more properties about square root that we want to recognize. So how about the first one right here? I'll call that part A right here. So square root of 9 times square root of 4. So now we have the problem have to keep getting more advanced and more advanced and more complicated. We have to, in other words, we have to keep moving forward and be able to learn more about square root. So earlier problems, I was just working with problems where it's just very elementary problem. We take the square root, simply just take the square root of this number, take the square root of that number. Okay? But now when you're observing this problem right here, taking the square root is not the only work. And in other words, taking the square root is not the only operation. Here, aside from taking the square roots, it looks like there is also a multiplication. Okay, there's a multiplication involved here as well. So the way how I'm seeing this, in this problem right here, there are two operations involved. There's taking square root, and there's also taking a multiplication, a product between the two work right here. Okay, so now I have to mention one thing. This is a little side note that allow me to start mentioning it, and it's also a fact. So square root is an operation. From now on, from this point on, square root is legally an operation. So up to your learning at this point, we have learned addition, subtraction, multiplication, division, exponents, and parentheses. And of course, I haven't mentioned about the order of operations. But now, aside from those operations I've mentioned, then we adding in another. So in our bank of operations that we've learned, this is another. The square root is another operation to be added into our library or to our bank of operations. And so the fact I was about to mention is that, all right, so what I just wrote down right here as a fact right here, square root now is understood as an operation. Square root is of higher priority than multiplication. Higher priority than multiplication. So with this statement right here, it leads us into the way of how we're working with this particular problem right here. So I see that we have taking square root as one operation being involved, and we have multiplication as being involved right here. So according to the facts right here, then taking square root is of higher priority. Higher priority means now between the two operations, we must do those square roots first. So now square root and square root, of course, they have equal priority. So that means for a problem like this, we are required to do two separate square root problems. So in this way, the way how I see it, remember, square root is of higher priority. So I'm doing the two square roots first. So square root of 9 comes out as easy as that is for anyone. Square root of 9 equals 3. On the other hand, the other square root right here, square root of 4 will give me a 2. So now I have done taking the square root of the two values here. Now the next step is to multiply, because square root is of higher priority. And so now multiplying 3 and 2, I'm getting 6 as the usual calculation goes. So what we've learned from this little problem is that square root is of higher priority than multiplication. But so, even though I said so, be aware and be completely aware of some situation like this, and it will happen quite often. Let's say I have a problem that looks like following. Take the square root of 9 times 4. Okay? Now, even when I'm saying it, it may sound a little confusing right here, but the way how it looks right here, making it the best, the clearest to understand. We take the square root of that product. We take the square root of that product, and the product is between 9 and 4. And so behind the scenes, this means, it means we have to put 9 times 4 as one group. So now the parentheses was not initially introduced, but now that's what it means. When you take the square root over a product right here, that means we group the product in parentheses. And so parentheses is, according to what we've learned by far about PEMDAS, about the order of operation, parentheses stays the highest priority. So no matter if we learn a new operation, it's still, the new operation is still having lower priority than parentheses. So that means whichever being grouped inside parentheses, we have to finish that first and take the square root at the final step. So here in this case, see, that means having the product being done in the grouped parentheses. And then whatever the answer that turns out, it's going to be square root of whatever that product is. And so in this case right here, that means, of course, I am holding on to the square root. 9 times 4 inside has to be done first. So that gives me 36. And now the square root is taken after. And that now gives me the answer equals 6. So that's my argument about this problem right here. So be extremely cautious about square root of a product. It really means 9 times 4, the products must be taken first, because there's a grouping that, even though was not written even though it's not specifically indicated initially, but that's what it means right there. And then so now it's making things clear. We have to get things being grouped, taken care of first, and then the next operation comes the forward. All right, so I still didn't want to leave problem number 3 yet. So after we have learned about, after we have had some experience from problem part A and problem part B from the same problem right here, then I would like to drive that, I would like to use that and utilize that into another little problem right here. So again, square root is of higher priority than multiplication. So in this case, I have a value 2, a value that's already known, 2 times the square root of 14. So in this way right here, I have a product. This product is between 2 and the square root of 14. But according to this fact right here, we have to take the square root first to know what's that actual value of the square root of 4 is. And then we do the multiplication after. So that means in a way how we working through the steps right here. First step, I have to take the square root of 4. That gives it a 2. That makes it a 2 right here. Square root of 4 becomes 2 or equals 2. And then the other 2 still got held on to. And now the next step is we're going to multiply. So like I said, we took square root first and then we multiply. So now 2 times 2 equals 4. Okay? Because now be extremely careful. It has never been true. It has never been true that 2 times square root of 4, and sometimes I may even skip the multiplication dot right here. This product right here will never be equal to the square root of 2 times 4, which makes it square root of 8. This is so not true. So be fully aware of that. So your actual answer is 4, and the way how we got there, see, 2 times square root of 4 equals, the first step, we took the square root first. We took the square root operation, and then we took the next step, the multiplication operation. And so in that way, allow me to get into something like this. Still, I didn't want to leave problem number 3 yet. So what it reads here is we have a product. The way how it reads 2 times the square root of 5, or for short, people say 2 square root of 5. Okay? But what it truly means, 2 times square root of 5. That's what it means. But then again, we are recognizing there are 2 operations being involved here. There's taking square root and there's multiplication. And so again, square root is of higher priority than multiplication. So that means we have to take the square root of 5. But from earlier discovery problems that we have done, square root of 5 is classified as an irreducible square root, or in other words, because 5 itself is not easily recognized as a perfect square, and it never is a perfect square. And so taking the square root here is doing nothing good but just giving you lengthy decimal. So we avoid doing that. We prefer, remember, we prefer to keep square root in exact expression. So that's the best we can go right here. Square root of 5 is square root of 5. And so really, square root of 5 is already in its most computed form. Square root of 5 is left exactly the same. 2 square root of 5 is left exactly the same, 2 times square root of 5 right there. But that's all we can do right there. And the worst mistake is to multiply the 2 with the 5 inside the square root and then take the square root. That's violating this fact right here. All right, so now in problem number 4, allow me to bring in the following operations that works together with the square root right here. In part A. All right, so what we have here is a fraction, and in this fraction the numerator is a square root of 100, and in the denominator it's a square root of 36. Okay, so what I want anyone viewing this lesson to understand is that in a problem like this, in a computational problem like this, we have square root as an operation, and we also have division involved here. Okay, we have square root and we have divisions involved. So the way how it means here, and see, so now fraction has been long understood and known as a division. So this exact fraction right here can be understood as the square root of 100, and we're dividing that by square root of 36. And so now it really showing clearly all operations being involved in here. So now I have to bring in another factor here. All right, so another fact I would like to introduce, and that will explain the way how I will eventually solve this problem or compute this problem right here. The fact here says square root is of a higher priority than division. Square root is of higher priority than division. So now bringing that fact into this problem right here, how I'm seeing it, in the way how I'm seeing it, there are two square root operations involved right here, and there's a division. So now with this factor here, that's the driving key for us. The driving key says we need to first work on the square root, finish, or another way of saying finish out the two square root operations before we can divide in that order. And so now there's two square root operations for the first one, and these are, I tend to work on the left hand side compared to the right hand side one, but these are having about the same exact priority. So, or you can think about we working on these two square roots simultaneously. And so simultaneously, or at the same time, square root of 100 come out being 10, square root of 36 come out being 6. So truly we have a division between 10 divided by 6. So I have done now square root taken care of first. And then I'm going to start doing the division. And again, this division here means the same as, putting that as a 10 over 6. And so, truthfully speaking, I've been writing these two steps right here for extra clarifications and explanation. But right from this fraction right here, anyone can just think about in your thought process, think about that's simply just equal to the next step, the square root of 10. The next step is just 10 over 6, simply because, see, I could have just written that and explained that in a way that the square root of 100 in the numerator is a 10. The square root of 36 in the denominator there is a 6. And now we produce a new fraction. It's like a new the division problem. And now the division problem truly is as a fraction. Now we can just simply reduce that fraction, making it 5 thirds. Yeah. All right. So that's how we performing a computation when roots, square roots, and divisions are involved. All right. So we have been now at this point knowing that square root is of higher priority than division. But even so, there are still times that we got to watch out for it. So let's look at this computational problem. There is division involved in the problem. There is taking square root. And I still want to put this computational problem among those problems I call problem 4. Yeah. So anyway, here's how I'm seeing it. Now, you can observe and see that the entire fraction is being put inside of the square root. So what it means here is that we have to do the division between 125 first in the group, and then we take the square root. So now we've done problem 3, and now we've done problem 4. Problem 3 part B, I introduced some problem where there's grouping involved in the same way over here. There's the parentheses is here indicating grouping. So in that way, we have to finish out the grouping. So grouping in parentheses always been done first before anything else can be carried out at this point. And so in this case right here, the way how I'm seeing, I must divide it 100 by 25 right here. So the step here is saying that dividing the division happens first. So 100 divided by 25 gives me 4. And now that we take the square root as the next step right here, that gives me square root of 4 being equals 2. And that's our final answer. Okay, and for short, this step right here is just my explanation for you to understand the meaning of the expression, that fractional expression inside of the square root. But a lot of times you can actually skip this step right here in your brain process. Just think about that. Means we have, as a grouping, we have to do the inside part first. So finish out that division problem inside. Finish out the division problem inside the square root. And then we take the square root after. So as a shorter way of doing the problem, square root of the fraction 100 over 25 can be just simply done as, in the next step, square root of 4. That is because we have done division first. 100 divided by 25 equals 4. Then we take the square root. Then the answer after square root is a 2. And you know, fraction is always something that you have to pay extra caution. So I don't want to leave problem number 4 here yet. And let me bring in another problem very similar to part B that we have done earlier. And so here in part C, we have a square root of 9 over 16 right here. Okay, the square root of 9 over 16. So we have seen the arguments, the logical reasonings already. But in the earlier problem, the fraction was, see, and that's the challenge and the thing that we have to pay extra caution right there. Sometimes fraction reduce nicely into a whole number. But some other time fraction does not reduce. For example, right here we already had a fraction. Right here we already had a fraction that's already irreducible. We can no longer reduce this fraction right here, unlike the earlier case. And so technically there was already a step where you took the division between 9 and 16, but 9 and 16 does not divide out evenly, and that's why it becomes it stays permanently as a reduced fraction here. So there's the division process was already done, and that gives me that hard 9 over 16. So now, well, how do we take the square root of something like that? Because the division already gave you just 9 over 16, and we're not going anywhere with that. So taking the square root of the 9 over 16, here's how I'm seeing it. Your math, your common understanding about math up to this point is strong enough for that. I see the 9 over 16 inside my square root here can be understood as a 3/4 all square. Okay, 3/4 all square. And so now seeing that as a perfect square, so yes, a fraction is a number too. So here I see that as a perfect square of 3/4. So 9/16 is a perfect square of 3/4. And so now taking the square root of a perfect square, now we treat that just like a number where you took square root of a perfect square 25, or you took a square root of a perfect square 100. So now how do we take the square root of a perfect square 3/4 all square? The answer comes out simply 3/4. The square is gone. And that's how we're doing it. All right, so now allow me to bring in another problem right here where we keep exploring further into the properties and the understanding of a square root right here. So let me bring in out the following computational problem. All right, so in this computational problem, this simple computational problem, we're looking at square root of 9 plus square root of 16. Square root of 9 plus square root of 16. Okay, and so as far as for computation purpose right here, I see that there are two operations involved in this problem. They are taking square root and they are adding. There are addition and there are taking square root. And so with those two operations being recognized here in our problem, allow me to bring in the following facts right here. All right, so allow me to bring in that fact right here. That's one fact, but that works for both operations. Square root is of higher priority than addition and subtraction. So square root is of higher priority than both of these or any one of these. Okay, addition or subtraction. All right, and so in that case, our problem here involves addition and taking square root right here. So in that way over here, with the fact I've just now written down right here, that gives us some clear instruction of how we go. So in my next step, it tells me that in my thought process, I have to finish out taking the square root on these two parties first. So the square root of 9 is a 3. At the same time, the square root of 16 is a 4. And now we can add these two. So after taking the square roots, we can add after. So now I'm adding 3 and 4 over here. That gives me 7 being the total, the final answer. Okay, and so that's how we're working with a problem where addition that comes together with square root together. Okay. All right, so allow me to bring in a quick computational problem again in part B of our problem 5 right here. Let's say we got square root of 4 minus square root of 25. So again, I'm repeating this fact that I have written on the board right here. Square root is of higher priority than subtraction as well. Okay, so in this case right here, I recognize subtraction that's being mixed together, being operated together with square root. So in that case, I have to finish out the 2 square roots involved here first. So here I'm looking at square root of 4 giving me 2, square root of 25 giving me 5, then 2 minus 5, that will give me minus 3. And that is our final answer. So again, this quick and solid the subtraction problem right here points out that fact that square root is of higher priority than subtraction. All right, but still, even though I said square root is of higher priority than addition or subtraction, there are still times where we need to work with things a lot more cautiously. We need to be paying extra attention right here. So in this problem right here, we got square root of the sum, square root of the sum 9 plus 16. So in this way, in the way how I see it, allow me to bring in the interpretation right here. It means 9 and 16 are being grouped. 9 plus 16, that sum between 9 and 16 is being grouped in parentheses. And then we take the square root. So that's what it means right here. And so now, formally speaking, in that way right here, yes, I'm now, again, like what I've been sharing in the earlier discussion right there, then grouping parentheses will always be having the highest priority. And so here that means what in a mix, even though it seems like we recognize only 2 operations, the additions and the taking square root, but really there is also a grouping operation. We group and then we add. So group inside the add and then we take the final square root. So in that way, here's how I'm seeing it. 9 plus 16 being grouped together. So now that comes out with a result being 25. So that was done fast. And then the problem here instructs me to take the square root after that. And that's the reason why consequently in the next step it comes out 5. So here, watch out for that. When you have a sum that's being put inside a root right here, we have to finish out the sum. Then we take the square root. So finishing out the sum right here gives me a 25 in my problem. And that the reason we finish out the sum, because even though it was not written, it was meant to have parentheses that groups the sum together. And then after having that sum done, we take the square root. All right, and here allow me to still bring in another little computational problem in the big problem 5 right here. So here I'm looking at square root of a difference, 25 minus 16 right here. So again, I did say it clearly, square root is of higher priority than addition or subtraction. However, there are cases where we gotta open our we gotta pay more attention right here, and we gotta be more cautious right here. So thus here, the way how I observe and notice about that, we have the difference being completely put inside the square root. Okay, and so what it means here, what this expression means, there's a grouping. So even though it was not written, there was a grouping. 25 minus 16 being grouped to increase its priority. So now grouping these together, whatever it will come out, we're going to take the square root. So grouping this difference together is going to make its priority higher than the square root. So in that way, the actual problem turns out as following. So that just means this, but the way we're doing it formally, 25 minus 16 has to be done fast. So 25 minus 16 gives me 9, and then I'll take square root of 9. And the final answer comes out 3. Okay, and so this difference simply being the way we observed about it, it's being put inside a square root. So what it means here is we have to group that difference to increase its priority, and it becomes the first thing to be done. And then we take the square root. That's the instruction. And so in that way, I went ahead and subtract out 25 with 16 right there, giving me a 9. And then I took the square root after. That's how I arrived at 3. All right. And so right out from problem number 5 right here, we drew a couple of other fascinating facts right here and really deserves your attention. So allow me to call those facts some remarks right here, something that really you should pay attention closely to. Okay, so that's a couple of remarks I'm about to write down right here. So in that problem 5, part A, I brought in this computational problem. Square root of 9 plus square root of 16. Square root of 9 plus square root of 16. The answer we got at the end was 7. So I'm not going to roll back to the explanation anymore. But then in part C, I had a square root of 9 plus 16. And I spent quite a good amount of time explaining what it means and in terms of order of operations and all that. So this thing here, this computational problem came out being 5 for us. So apparently these two values, these two final outcomes, these two final values are not equal. Sometimes they may turn out equal. I'm only saying sometimes they may turn out equal, but the majority of time they will not equal. So the first remark, taking the square root of a sum is never the same, or is most of the time, or in general, different with taking the sum of two separate square roots. So I demonstrated that through the problems here, and we've seen the result, and we were clearly convinced that the two were not convinced, the two were not equal. So here, once again, we write it down. Generally, these two are not equal. All right, and so from problem 5 that I brought in right there, part D of the example, square root of 25 minus 16, we came out with the answer being 3. I didn't write this down in the earlier part, but square root of 25 minus square root of 16, we can learn from problem number 5, part B right there, and quickly get this calculated. The answer will come out being 1. And so these two results are obviously not equal. So that comes to another remark right here. All right, so the second remark I want to bring in here, the square root of a difference a minus b is generally difference with the difference between the two square roots, square root of a and square root of b. Okay, so these are the two remarks that you generally have to always keep with you right here, because I keep having my students falling into this trap and mistakenly set that equal with this. All right, so let me now bring in some observation. So the observation comes as following. 2 squared equals 4. That's easy. Minus 2r squared. This means minus 2 times minus 2 in our understanding of basic arithmetic right here. Minus 2 times minus 2, a negative number times a negative number, positive 4 again. So here, in a way how I'm seeing it initially, see there was a 2 squared, positive number square. Okay, positive 2 square, that gave me 4. Minus 2 square, see, minus 2r squared. That's why I put it in parentheses, equals 4 as well. And so in that way right here, now think about the way reversed, because now we're learning about square root here. The square root of 4, when we're saying square root of 4, is that, are we intending for the answer 2 or negative 2? That's the question, that's the worry. Because see, both of these, after squaring gives me a 4, so now simply just, with this instruction, taking the square root of 4, are we really getting 2 or negative 2? We keep getting advanced and more advanced into our understanding of square root right here. So now what I'm about to say is really a convention. So now the truth is, when you say square root of 4, so when it says square root of 4, it refers to the positive square roots. So just that simple, just simply that symbol right there, it refers, right, to the positive square root. So now keep in mind the square root sign right here, without nothing else, just the square root sign as we've been knowing since the beginning of the lesson until now, that square root sign with a number inside of that, it refers to we want a positive square root. Okay. And so in that case, there will be time that you are given an expression like this. So now anytime you see a negative sign indicated with your square root, so indicated in front of your square root, this is the one that means we want the negative sign, the negative square root right there. So this one here, see, let me open the quick little the optional parentheses right here. If indicated, see, if that negative sign is indicated with our square roots, that will refer, or that refers to, okay, negative square root. And so in that case right here, as a final generalization, square root of 4 equals 2. And if indicated negative square root of 4, that's where it's indicating that we want the answer negative 2. Okay? And so it's sort of like a default one. Just the default one is a positive one. And then if needed, we indicate a negative right here. That's indicating, hey, taking the square root of 4, but I want a negative 2 answer. All right. All right, so now we come to the following generality right here. So generally, square root of a squared, see that symbol that it was indicating, the a itself could be a positive number or it could be a negative number. That's why now more like a general instruction. And taking the square root of a perfect square, we means the positive number. That's why there's absolute value right here, because the value itself of the variable, the number that we take right here, can be negative from the beginning. And so taking the square root of an a square, where a here could be positive, could be negative, the answer has to come out being the positive, and we're indicating positive by having that in absolute value. So generally, square root of an a square equals absolute value of a for all values of a. So the phrase all values of a right here indicated that the a itself could be positive or a itself could be negative. But then from that understanding, furthermore, we narrow it down to a more specific case right here. Now if a is already known to be a positive or the zero value, non-negative, then taking the square root of a squared will equals a. So this is clearly true, but only if the value a is known to be greater than or equal to 0. All right, so in that way we've just learned what we have just learned from on the computer screen right there, and allow me to give an extra clarification on what we did in some of the problem earlier. So back to problem 4, part C, we had the following computation problem. Square root of 9 over 16. And I was explaining all of that about how 9 over 16 was an irreducible fraction. And in the end, see, I had to explain that the only way we could do about it was to recognize 9 out of 16 as a perfect square of 3/4. So 3/4 as the perfect square of 3/4. So now here, after what we've learned on the computer screen, we're seeing that taking the square root of a perfect square will come out equal just the number or the fraction without the square. Okay, and so we can now learn that property as one thing that we can effectively, one way to directly calculate square root of anything. Okay. All right, so now we arrive at our first example over here. So an example for me in this video lesson is where I just bring in all of what we've learned. A problem that I brought up right here, that those problems that I call problem 1, problem 2, problem 3, they all for us to, we go through the problem, we try our best with our new learning. And then we recognize from our properties that right there through those problems, right there, we recognize more details and more properties. And now after we have learned those properties and those details right here, we're gonna start to creatively work through some more problem solving right here. That's where I call that examples. So examples is where we can creatively apply our skills, what we've learned, and bring that into a more advanced problem right there. So here in example 1, I want to introduce a kind of problem where we're asked to simplify All right, so the first problem in example 1 that I'm doing right here, we are asked to simplify square root of 49x squared. So square root of 49x squared. Up to this point, we have learned that as long as we can re-express our expression inside of the square root right here as a perfect square, then we're good to take the square root. So I remind you about that on scratch work right here. I remind you about that problem earlier, 9 out of 16. And so before taking the square root, I recognize the entire expression inside the square root here as a perfect square. So that was 3/4 all square right there. And now I can just easily take the square root, and the square root come out to be simply just 3/4, and the power 2, the square, got canceled away. Okay, and so in that philosophy, that's how I'm bringing that into this problem, and we came up with that generalization prior to giving out the example over here. So after realizing all of that work and having that fundamental understanding, all I need to do is to be able to recognize the 49x squared here as a perfect square before I'm taking the square root. So now the square root operation is still here, but the entire 49x squared, in my next step, I see that as 7x all squared. And then your understanding from the previous class can help into explaining why I come from 49x squared to 7x all squared. So that you must bring in some of your understanding from the previous class. But now the point is, now I have expressed my expression inside the square root right here as a perfect square. And so now upon seeing the perfect square inside of my square root, the final answer after taking the square root of a perfect square will give me simply just 7x right there. Okay, and now allow me to go back to this problem right here and include an additional instruction right here. Let's say we want to simplify, but there are variables right here. So the x itself could be positive or it could be negative. So for now, let's all assume, right? Let's say assuming, all right. So let's assume all variables are non-negative. So that means this x right here is assumed to be greater than or equal to 0. And that means we don't have to worry, we can just go direct. We don't have to worry about putting in absolute value. Okay? And so there you go, square root of 49x squared, square root of the product for 49x squared. What I did, I simply just recognized that 49x squared as a perfect square, 7x all squared. Once recognized that, taking square root is extremely easy. Just cancel out the square, we arrive at that final answer. All right, so allow me to bring in another problem right here. How about we're asked to, or we're instructed to simplify the square root of 144x to the 8th. Okay, and so very similar experience. I just want to bring in a different problem right here where the power doesn't show a square so easily. So, but again, the philosophy here is to be able to recognize that entire expression as a perfect square. So here's how I'm seeing it. 144x to the 8th is understood as 12x to the 4th all squared. That's how I see the expression inside the square root can be expressed as a perfect square. And then the square root will be taken after that step right there. You may skip this explanation if you feel comfortable already, but in case your previous learning from your, previous class has faded away, then allow me to explain a little bit. But like I said, anyone who already had understood the reason why I did that, then you can skip this, the optional explanation. But all right, 144x to the 8th. 144 is easy to recognize as a 12 square. So I can see 144 is a 12 square times now x to the 8th. It's a little more challenging now, but x to the 8th is x to the 4th, but all square, because the 8 here is 4 times 2. So really x to the 8th equals x to the 4 times 2. And from our previous learning in the previous class right here, when we raise that to a power being a product, we can purposely write that as x to the 4th all squared there. So this is from previous learning, and I'm just simply reminding you that. And so from this point right here, now with your past learning, again, in case it's fading away, when we have two expressions with the same inner products with the same power right here, then we can regroup them as a 12x to the 4th and all square. And that is the reason how I went so fast from 144x to the 8th into 12x to the 4th all square as a perfect square. All right, so now that anyone has agreed with how I made that, the next step comes out as easy as just rewriting the 12x to the 4th with no square here, because the square root will cancel out the square right there. And then this is our final answer. So square root of 144x to the 8th equals to the square root of 12x to the 4th all square. And then taking the square root on the square, it gives me just that expression before the square. All right, so here we're at example 1, part C. The same example 1, but let's bring in one more problem right here. So here I'm looking at square root of 25a to the 6b to the 4th. So we have the two variables involved here, and the point of these examples problems is that in generality you should even be expecting more variables, a lot more variables. But one thing that we've been doing commonly throughout the three problems so far is we got to be able to recognize the expression inside the square root as a perfect square. And so now in that way right here, I'm going to go ahead and look for a perfect square, or I'm going to look for a way to put my entire 25a to the 6b to the 4th into a perfect square. So now, after you've seen some experience and maybe also checked out my optional explanation I delivered earlier, then in that case, I'm saying that 25a to the 6b to the 4th is 5a cubed b squared all square. So now I have just expressed the 25a to the 6b to the 4th as a perfect square. And now the problem says we take the square root. So I'm taking the square root. And so now the square root, after taking the square root of a perfect square, the answer will come out as simply as just 5a cubed b squared. And that is going to be our final answer. All right, so here we're at our example 2 right here. Another the example where I want to show you how you apply your previously learned knowledge, your previously learned details about square root into doing some problem where it start taking some creativity in applying it. Okay, so in our example 2, it's simply an evaluation problem. We want to evaluate in part A right here. All right, so I want to evaluate the square root of 121 over 16. So now this is not really an application. It's just coming straight forward from our learning that we've had just now, and it's quite similar to some of the problems that we've done demonstrating the idea. And so the only thing I want to emphasize now, whatever expression inside of our square here, we need to be able to express that as a perfect square expression. And so 121 over 16, we have a fraction here. This fraction here is sadly irreducible. But now, thankfully, 121 over 16 can be recognized easily as 11 over 4 all squared. And so that's what I've just now done to the fraction 121 over 16. I recognize that as a perfect square of another fraction. So it's a perfect square of 11 over 4. And now the problem was asking us to take that square root. So now we're going to take the square root after. So the first step, I wrote these problems in a certain order of operation. But first I recognize that into a perfect square. Then the square root carries along. So the real next step now is we're going to take square root. So taking the square root on the square here gives me 11 over 4. And 11 over 4, before squaring that, we already saw that it was a positive number. So taking the square root, it's just simply coming out the way it is, 11 over 4. All right, so part B of the example is another one similar. However, it adds in a little more experience. That's why I said these examples are where I can show you the work that applies the understanding, but with some more creative work like that. And so there are so many directions you can head out. But so now keep in mind, in the way how I'm seeing it, we have learned from the earlier part of this video lesson that we have to finish out the 72 over 98 first before we take square root. The division inside of the square root here has to be done before taking the square root according to the order of operation I've mentioned earlier. So in that case, here's how I'm seeing it. At least the fraction here can still be reduced. It's better, I mean, it's a little more work than the earlier problem in part A, but it shows you that we can do something before we take the square root. And so I'm going to put in one extra step. I'm going to reduce 72 out of 78 out of 98 right here. So 72 and out of 98 has a common factor of being a 2. So that reduces down to 36 over 49. So 72 over 98 is reduced to 36 over 49. And so I wrote that, and then after that I wrote down the square root. And then, so in my next step, now things comes back just like that fundamental we've learned. We have to be able to express this as a perfect square. And so the 36 out of 49 as a perfect square is a 6 out of 7 all square. And so now we take the square root. And now taking the square root of a perfect square, the answer will come out simply just 6 over 7. And yes, it's as easy as that. So the extra step I did here on top of the turning our expression into a perfect square, or before turning our expression into a square, I reduced the fraction. All right. So let's look at our example 3 where we are instructed to simplify. All right, and the first problem in example 3 here, we are instructed to simplify the square root expression. We're having square root of 50x to the 10th all over 2x to the 6th. Okay, and so from what we've learned earlier in this lesson about order of operation, admittedly that square root should be done before division. However, the division here, remember, get comfortable with what I explained earlier in the video lessons. The fraction here must be done first because there's a grouping. The division here must be done before taking square root because there's a grouping. Okay, there's a grouping. And so that in that way, before taking the square root, I am going to go ahead and divide or simplify or reduce this fraction. So 50x to the 10th divided by 2x to the 6th. It comes out being 25 because 50 cancel with 2. Giving me a 25. X to the 10th cancel with x to the 6th. Give me x to the 4th. And so now the fractions represent a division. Now that division is completed out, is finished out into a 25x to the 4th. And that's a lot simpler now. The next step is to take the square root. However, now that we have arrived at this 25x to the 4th, again, we need to look for a way to rewrite this expression here as a perfect square. And so 25x to the 4th as a perfect square now is 5x squared all squared. So that fundamental about, hey, let's always rewrite, try your best to rewrite your expression inside the root as a perfect square. And we take the square root. So one more step and we're done here for this problem. So 5x squared all square inside the square root. So now taking the square root of that perfect square, the square here will be canceled away. So we remain with 5x squared right here. And this is our final answer. Okay, and so I'm bringing in all of the understanding we have previously discovered throughout the problems and the properties that we've discovered and listed them out. All right, so in part B of the example here, once again, we are instructed to simplify the square root expression. So again, the ultimate goal now, right before being able to take the square root, is we have to be able to turn our expression into a perfect square. However, before doing so, again, let's observe a fraction represents a division. So what I have here is a square root of a division. However, the division inside here means it's grouped together. So we must do the division before taking the square root. So with this division right here, there's not really anything we can simplify or anything like that. So in other words, the division problem here, the fraction itself, the rational expression itself is already at dead end. The fraction is already at its most reduced form here. So the best way I can do, again, let's stick back to the original plan. Get that expression here rewritten as a perfect square. So 49x to the 6 all over z, y to the 4th, z to the 8th right here. That can be re-expressed as 7x cubed over y squared z to the 4th all square. That's how I have re-expressed my fraction here as a perfect square of another fraction. And so now the next step is to take the square root. And that will become just simply, in the next step right here, the square root will make the square be cancelled. So now we're going to have 7x cubed over y squared z to the 4th power. And that's how we're done with that particular problem right there. And so this explanation I'm giving here is optional in case your learning from the past courses has faded away right there. But I just want to explain the reason how I got that expression 49x to the 6 over z to the 4th, y to the 4th, z to the 8th. I just want to explain how that becomes a perfect square so quickly right there. So 49 is understood as 7 square. X to the 6. Notice, after noticing that even power, and you have seen from my earlier explanation that x to the 6 even power now can be explained as x cubed all square. So anytime you have an even power, you can turn that into a power 2 right there. And then the y to the 4th, another even power, it's a y square all square. And then z to the 8th, that even power can be expressed as z to the 4th all square. And so now all together it becomes, see, it's a power 2, power 2, power 2, power 2. So these are all, and so how about one more step? I can rewrite the numerator here as 7x cubed all square. And I can also rewrite the entire denominator here as y squared z to the 4th all square, because these are having like powers, and in a product these are having like power in a product. And so now I can even further see these are now in a quotient having like power in a quotient. Now I can put them as 7x cubed over y squared z to the 4th all square. And that's how I can explain for this 49x to the 6 over y 4th z to the 8 into that perfect square so quickly.